welcome to this lecture. In this lecture, we are going to talk about the fixed bed type regenerator analysis, and in the last class we have talked about the different type of regenerators, and in that one we have talked about the valve type or the fixed bed regenerator, and we also talked about the rotary type regenerator. Here in this lecture, we are going to talk about the analysis of the fixed bed type regenerator, and in that context we just want to look into the actual system where this kind of regenerators are in use, and it will be easier for us to analyze it if we look into the action or the operation of this particular type of exchangers. So, for that we have taken an example of a cryogenic application, particularly it is called the pulse tube refrigerator, where we find thin walled empty tube is periodically pressurized and depressurized. Here this is a pulse tube where we have a thin walled empty tube, and on this side we have a hot end heat exchanger, and on the other side we have another cold end exchanger. This is the cold end exchanger, and this is periodically pressurized and depressurized with the gaseous helium. Now, if we look into this operation, you will find that there is a small valve, and this valve we call it as a rotary valve. So, this rotary valve periodically sends high pressure gas into the system, or after one cycle it will connect it to the suction side of the compressor. In one cycle it connects it with the discharge side or the high pressure side. In one cycle, in the alternative cycle, it will connect it to the suction or the suction or the low pressure side of the compressor. So, alternatively it connects it to the high pressure and the low pressure, and between the pulse tube or the empty tube and this compressor we have one regenerator. So, this is the regenerator, this is of fixed bed type, and we find that this regenerator is basically what it is doing is it is trying to connect. You see, when the high pressure gas is coming from this end to this end, this will allow the gas to pass through this. If it is in this configuration, so the gas will be high pressure gas will be coming from this end, and it will pass through this regenerator, and then it will come to this pulse tube. So, now in one cycle what is happening, this high pressure gas is coming to this side, and this is at say the hot TH temperature, and on the other side when it is in the steady state operation, we will find that this is the cold side and this is also at the cold side. So, here we add the refrigeration required refrigeration QC. So, now in this cycle, so what is happening, the high pressure gas is coming and flowing through the regenerator. So, this gas is at high temperature, and by the time it is coming over here, it is passing to TC. So, while passing through this regenerator matrix, it will be heated up, this matrix will be heated up, and the gas in turn will cool down to TC, and at the end of this cycle what we will find that this gas is coming over here and getting expanded in the other cycle. When it is connected to the suction side of the compressor, we find that this cold gas is coming to this side and it will be passing through this one. So, this gas is at TC or slightly lesser than TC, and this gas is going back to the suction side of the compressor via this regenerator. When it is passing through the regenerator, it will pick up the heat it has left earlier in the earlier cycle to this regenerator bed. So, now we can understand that in one cycle the hot gas is coming generally this gas is helium, gaseous helium, and this pressurized gaseous helium will be passing in the one cycle through this configuration, and in the other cycle when it is getting discharged, this low pressure helium or expanded helium will flow through this regenerator, and in this configuration it will pass through this one and go to this one. So, this is how it works in both the cycle. Helium is the gas which is passing through this regenerator. This is of our concern at this moment. So, in one cycle we will find that pressurized gaseous helium flowing through this regenerator. In the other cycle we will find that the low pressure helium, expanded helium from Tc, it will move to Th in the ideal condition. So, this is what is the configuration of a fixed bed regenerator or the principle of working in the pulse tube refrigerator operation. This is the basic pulse tube configuration. Now, if we move with this basic knowledge of this fixed bed regenerator, if we now move to the next its analysis part, we understand that in one cycle the gaseous helium or the hot fluid stream is flowing from one direction to the other direction, and in the other cycle the cold stream is flowing from this end to this end, from x equals to L to x equals to 0, this end. So, as you can understand that this hot stream and cold streams are alternatively flowing through this direction, and the direction is reverse in nature, counter current in nature. That means, in one cycle they are flowing from the hot stream is flowing from this stream, this end to this end. In the next cycle the cold stream is flowing from this end to this end. So, the configuration is basically counter current in nature. So, now we have if we look in detail about this elemental area between x and x plus dx. Basically, it is a one dimensional model, and here this is x equals to 0, we have x equals to L. In between we have taken some region bounded between x and x plus dx. Now, with that we find that some let us assume that the gas hot stream is flowing through this and it is when it is flowing through this medium, it is moving out with a temperature of T plus del T del x into dx, and it is the mass flow rate of the hot fluid stream may be m dot. Now, if you look into this one this configuration, what we find that we have some solid particles and we have certain amount of void. So, this is the solid particle and this is solid particle, and we have void. In the last class we have talked about it. So, the void is it is given by E v, that is the void fraction. So, now if we look again into this part, we find that we have some amount of heat transferred from the fluid to the solid part. So, if it is hot fluid, we find that the hot fluid is giving heat to the solid particles, and this is the amount of heat transfer, where H is the heat transfer coefficient, T is the temperature of the fluid stream, T s is basically the temperature of the solid particles or the matrix temperature. And we have considered that for the length L, we have some area associated with it is A, and so in the length dx we have A by L into dx area associated with this region. So, H into A by L into dx is the area, and this is the temperature difference. So, that is the amount of heat that will be transferred from the hot fluid to the solid particle. Now, In turn, what will happen because of this change in of the, as the hot fluid is giving the heat to these solid particles, its temperature is, or there is a change in the enthalpy of this gas. And in turn, as the gas is flowing through, it is giving heat to the solid particle, and whatever gas which is there inside, some part will be, the energy will be stored in this void fraction. That is, we find that this is the amount of energy that will be stored within this one, within the gaseous volume. What is that gas? That m part, that is, that is equals to the void fraction, that void where we have the gaseous part and multiplied by the Cp of that one, that is Cp is the gaseous Cp, and mass is the particularly that is equals to the rho of the gas and V of the gas. So, that is the void volume multiplied by the actual or total volume of that system. So, we will come to that part to how to evaluate that part. And so, now we can understand that within this element we will have this much amount of gas associated with it, and that is how the energy will be stored within that volume. And with this knowledge, this is the energy balance. We are talking about the fluid, and we find that the gas is moving from one end to the other end. It is giving some heat to the solid, and there is some change in the overall enthalpy of this fluid, and some amount of energy is getting stored inside the element of this gas. So, if we now write an energy balance, we would be able to make an energy balance for this one. And next is how do we write that one? How do we write that equation? So, this is what is entering. So, it is m dot Cp into T, and this is moving out. So, it is m dot Cp, then you have T plus del T del x into dx, then this part is also moving out. So, it is H into T minus T s, then you have A by L into dx, and that is exactly what is it is getting stored in it. So, it is m into Cp, and this is del T by del tau, that is equals to the time within this time tau. This is the energy that has been stored in this element. So, that is multiplied by dx, and that is exactly the energy balance for the fluid stream. Now, the same thing we can try to look into, for the this is for the energy balance. As we have just noted in the previous slide, that was the energy balance we have written. Now, if we go to the solid part, we find that the solid is receiving some amount of heat from the hot fluid, and that is given by this amount. So, this is basically H into T minus T s A by L into dx. That is what we have learned, that this fluid stream is giving this amount of heat to the solid. When the solid is receiving some amount of heat, what happens to the solid temperature? Its temperature is going to rise. So, if we say that the solid is having a temperature T s, we know that del T del tau, it will be the temperature rise, and if we now look into the energy associated with it is del T s del tau, as I told you, and multiplied by the m s and C s. So, if the mass of this element is m s and C s is the mass associated with it, then we have dx, the elementary length associated with it, then we can write it, we can equate it with this term and this term, and we can find the energy balance equation for the solid. And in that case, we will have, if we write both the equations, we find the governing equation for the fluid stream. If we rearrange them together, we find something like this. So, this is particularly the amount of heat that has, we have talked about the hot fluid in the cold cycle. I mean, when the cold fluid stream is flowing through the regenerator. So, this is the amount of heat either received by given by the hot fluid or the received by the cold fluid. Either way, and this is the amount of the stored energy in it, and this is the change in the enthalpy. So, that is what is for the fluid. Now, if we look into the for the solid part, we have, this is the equation written for the solid part, and so these two equations are the governing equation. And when we write any differential equation, particularly involving the time and space, we have to use some kind of boundary conditions or the initial conditions to solve this equation. So, these are the boundary conditions as we have written in the or the entry fluid entry condition, as we have written it here as part the Ackermann's cryogenic regenerative heat exchanger book. And here what it is telling is that when it is entering the regenerator. So, this is entering at a temperature of TH. So, this is this tau dH, basically this tells about the tau d is the dwelling time for the hot fluid. This entire duration, when it is entering this regenerator, that means we have, if you remember that we were talking about the regenerator, it is the hot fluid was entering through this regenerator, and this is at x. If we say that this is equals to x equals to 0, at x equals to 0 it is entering, and it is entering at a temperature TH. We have said that that end is at TH, the other end is at TC. So, the other condition for the cold fluid stream when it is flowing in the other direction. So, this is at it should be either at x equals to, it should be XL, or if we consider for this direction also, if we change it to x equals to, this should be x equals to L. So, for this entire dwelling time T tau dC, we have a temperature, it is entering at Tc. So, now the initial or the steady state condition is basically what we mean is that what is the temperature of this bed, how it is behaving, or the temperature of this matrix, basically we wanted to calculate. So, here we have for this earlier we talked about at x equals to L, but now we are talking about L minus x. So, here you see at x, at a location x for this hot fluid stream, it is at any distance x, that is equals to, that is same as what it was there in the previous cycle at the same location. So, if the gas was flowing and this is say it was entering at TH by the end of this cycle. So, it will leave the bed at a particular temperature. So, that is what is the initial condition for the other fluid, like when the cold fluid stream is moving through this one. So, that finds that the bed is at that particular temperature at different location. So, that is what is the initial steady state condition for the cold fluid. Similarly, when the cold fluid is flowing in this direction, at the end of the cycle it will leave the regenerator bed or the matrix at a particular temperature. So, that temperature profile, that fluid, the hot fluid, when it has to come in the next cycle, it will find that the bed is prevailing or the bed is having that temperature profile at the end of that cycle or at the beginning of that cycle, but it has what it has been left by the earlier cycle, or the fluid it has left it in that condition. So, that is how is the I mean the boundary or the initial conditions, but as it can be understood that it gives I mean quite I mean makes the analysis or the solving these equations is a bit complicated, but we will not look into that details of that solution. But before just we will just have a look into this slightly more in details. So, we basically define two dimensionless parameters. One is the dimensionless distance and the dimensionless time. One is z equals to x by L, and then eta, that is equals to dimensionless time. So, this makes with this transformation with this change in variable or dimensionless parameters, we can write the governing equations to this form, and the other equation will take this step. So, finally, if we apply those boundary conditions and if we try to solve this one, I will suggest the readers or the students to, if someone is interested about this one, they can look into the Academans regenerative heat exchanger book, or I mean for the detailed analysis of this. But if we look at this solution of a ideal regenerator, we find that that I mean at the beginning if or at the end of this one, how the cold fluid or the matrix is I mean how would be the temperature and the distance I mean relation. So, here we have the temperature or the reduced temperature, and on this side we have the dimensionless distance, longitudinal distance, and this is how the cold fluid is entering to this heat exchanger, and we find that this is how it is, it has, when it has started, this is the temperature of the gas, cold gas flowing through the regenerator, and by the time the end of the cycle it will be coming to this temperature, and this is the matrix temperature, or this would be the, at the end of the cycle, this would be the temperature of the matrix. So, on the other way or the other I mean end, we find that the cold stream initially it is flowing from this end at the beginning of the cycle, it is like this, and as time passes, by the end of the cycle it will be coming to this condition, whereas the matrix will be in this region. So, this is what is happening in the regenerator, and this is of course the balanced condition and ideal regenerative action, where we do not have any axial conduction losses and etcetera, we have not considered. But if someone is solving that equation and with the boundary conditions applied, as you have said, one can solve and get this kind of I mean temperature profiles in the fluid as well as in the matrix of the fluid, I mean in the regenerator. So, we are not going into that details of calculating the temperature profile or the matrix temperature profile in this lecture, but rather we will be more interested to design or simulate a particular type of heat regenerator for cryogenic applications or any other application, where our job is basically to look for to simulate the regenerator under a particular application, or to try to design the regenerator for a given condition. So, for that we will look into the analysis or the suggestions given by the researchers, and we will look into particularly for the cryogenic applications where relevant to for this regenerator set cryogenic condition. So, let us look into the design part. So, for a counter flow regenerator, which is very common in case of cryogenic applications, we define the NTU, and it is given as 1 by C mean. C mean, again we have already learned about this C mean, that is the mass flow rate multiplied by the appropriate appropriate specific heat, and along with that we have the hot fluid and the cold fluid. This is 1 by HHAH, and this is associated the heat transfer coefficient of the hot site, and this is associated with the area associated with the hot site. And in general, if it is a fixed bed, most of the time this AH and AC are of the same area, and here this HC is the heat transfer coefficient associated with the cold flow. So, this is whole to the power minus 1. So, this is how we define the NTU for this counter current regenerator. So, with this basic definition, we will continue in the next lecture about the design or the simulation of the regenerator. Thank you for your attention.